This program is a presentation of UCTV for educational and non-commercial use only.
Good afternoon. My name is Paul Linden, and I'm the Director of the Sustainability Solutions Institute, under the auspices of which we run these Greenovation Forums. It's a great pleasure to see so many of you here, and we have, I think, a very interesting program for you. So I don't wish to take up any more time other than to acknowledge the sponsorship of this series from the Scripps Foundation for Science and the Environment, and we're very grateful for their support for this series, which are about water. And the current forum is about new sources of water, and we'll hear presentations about that. So it's my pleasure to introduce the first speaker, who's my colleague from Mechanical and Aerospace Engineering, Professor Sungho Jin. Professor Jin is a material scientist. He holds the Kazuo Iwama Endowed Chair for Material Science. He had a long and very productive career in Bell Labs before coming to UCSD, and he's a great innovator and colleague. So I hand over to Sungho.
It is a great pleasure to give this presentation this afternoon, and I'd like to thank the forum organizers for the invitation. Okay, so the title of the talk is Clean Tech Materials Using Nanotechnology. And the two topics that I'd like to cover are self-cleaning glasses, no-wash surfaces, and the second one is water treatment using nanotechnology. Okay. The motivations for doing research on water conservation, there are several of them. I'm a material scientist. I deal more with materials than devices. But one of the motivations was my colleagues here at UC San Diego. We have a group, environmental related group, led by Paul Linden, and some other colleagues in the MA department, and we end up doing discussions and collaborations often, and I had some discussions with Daniel Tatskovsky. He is another faculty in our department about how to stop the saltwater, seawater seepage into lake and things of that nature. So we may have some projects started. So anyway, in terms of a need to conserve water, we all know we have a water shortage problem in San Diego. As city of San Diego imports 90% of water, and with the possibility of mandatory cutbacks and rationing, things of that nature. So, and we also have a need to conserve environment and energy. The rapid accumulation of dirt on automobiles and house building exterior makes it necessary for frequent cleaning and washing of glass windows, exterior surfaces, automobiles, and so on, and which causes not only the waste of water, but the cleaning chemicals could contaminate the environment. And there are other areas. There are needs for safety, reliability in transportation and communications. These are not directly related to water conservation, but in some cases, like telecom antennas, when ice and snow accumulate, sometimes it causes problem. Airplane cockpit windows, you cannot have wipers on there, so you need to find a way to keep it clean. And also need to conserve energy in transporting of a huge amount of fluids, such as oil, transatlantic, oil pipe, water transportation, and so on. And there will always be some drag between the fluid and the wall of the pipe. And then when the pipe wall wears out, it's not the amount of pipe wears out, but it's the construction. Having to take it out and put a new one, which will be a hassle. And also it would cost more energy to push the water or oil through these pipelines. And so there are current and available techniques and how to prevent water from touching your surface. And so there are all sorts of current technologies, and we saw some opportunities for material science research in terms of making it super hydrophobic. In other words, the water does not stick at all, or super omniphobic. In that case, it's a combination of super hydrophobic plus super oleophobic. Oleophobic means oil does not wet. So if you make it super omniphobic, nothing sticks. So that's the goal. Okay. So one possible route for water conservation is to create super hydrophobic nano micro surface like a lotus leaf. We all know what lotus is. The leaves always ball up like this and it does not stick, and that's because it has some nanoscale structure. This is made by nature. So how do we maximize this on artificial surface so that water does not stick at all? And one approach that we use in our laboratory is to utilize aluminum and then do some electrochemical processing so that we have that kind of strong but water-repelling characteristics. So we try to come up with a convenient, low-cost, and high-throughput process. And so it's not only the materials itself, but we have to do some processing-related research as well. Okay. So this schematically shows a water drop, and this is what we call hydrophilic. The liquid wets the surface very well, and hydrophobic means it does not wear that well, does not wet that particularly well. And super hydrophobic means it does not wet, much more resistant. And so this angle, theta sub c, the larger the angle is, the better super hydrophobic. The idea is if you can make it 180 degrees, then you will touch only at point. Okay, so that's the aim of our research. And I'm not going to bore you with the equation, but the bottom line is the modeling has been done already. So the one structure that you want is basically a needle structure on like the bed of a nail, a bed of needle structure. And then the water can touch such a small, tiny area overall that it does not wet the surface. So this is, for example, if we take silicon and make a nanowire by chemical means, and we do some extra processing so that the entanglement is minimized. It's like, if you make this nanowire structure, and it's like, shampooing hair. Right after shampooing hair, the hair gets all tangled. But if you use special processing we borrow from semiconductor industry, what is called supercritical CO2 drying, then all these nanowires don't tangle, they separate each other, and then you get this beautiful 178-degree contact angle. Okay. So if you drop this water onto this kind of a nanostructure surface, it comes. Well, if we don't do any the hydrophobic coating, it stays hydrophilic. So water drops, and as soon as it touches, it gets absorbed right away. But if you put a little bit of a chemical, which makes it hydrophobic, then the water drop comes here, it touches it, it cannot wet, so it bounces off, and then comes down, touches again, it bounces a few times, and then just rolls over to the side. Okay? So this sort of schematically shows, in fact, we could not keep the droplet on the surface of this nanostructure, and we could not make measurement on contact angle. So what my students did was put a vacuum on the substrate so that it has tiny little bit curvature. Now we were able to make this droplet stay here and make contact angle measurements. Okay. So what are the potential applications for this kind of material? But the first In order to be viable for commercial applications, one should be able to make large area fabrication, and it has to be cheap. So vacuum processing, which we use in the laboratory often, is too expensive. So we are investigating a low-cost fabrication, large area technique, sort of a room temperature, what is called anodization, which is like a chemical etching under the influence of applied electric field. And we deposit aluminum, and then we do processing. And that's how we make this nanostructure. For example, if we take aluminum and then do chemical etching, we form these circles, holes. And if you keep etching, make these holes bigger and bigger, eventually all the circles touch each other, and then you got these guys left over. These are in the form of nanowires, for example. And this is an actual example of nanowires, and you can see the water drop does not wet the surface. It is good super hydrophobic material. We can manipulate, make this sharper or dull the way we want. And this is aluminum oxide coating, which is transparent because it's made so thin. Okay. So where can you use this? Okay, one example is clean free glass windows, high-rise buildings, and home windows. And in the US and worldwide, I see this everywhere. And if you don't have to wash windows, especially high-rise buildings, you save water, you save a lot of labor, and so on. And if we can make the automobile, car windshields, and we don't have to do a car wash, that will save a lot of water and chemical contamination. And as I mentioned earlier, durable pipeline for oil and water transport. And there could be other applications, such as airplane wings. We had an airplane crash like a couple of weeks ago in the East Coast when it snowed a lot, ice accumulation on the wing. They have to do de-icing. And if we make this surface, airplane wing surface, super hydrophobic, and ice and snow does not stick, then that will help a lot. And also there are miscellaneous applications like toilet bowls, which is not the cleanest thing to talk about, but people use ammonia to clean toilet bowls. And if you don't have to clean as often, then you don't have to use ammonia as much. Okay, and some people say, oh, how about kitchen utensils that you don't have to wash? Just rinse with water once, and that'll save a lot of labor for housewives and so on. Okay. So there are no clean window glasses, self-clean window glasses. The competition is they basically based on titanium oxide type, and it's hydrophilic. So the material decomposes whatever sticks there, organic stuff, but it requires water or rain to wash it away. So our approach is if we make it really repellent to water and oil and everything, nothing sticks in the first place, that you don't have to wash it off at all. Okay, so that's our approach. So I sort of described using nanotechnology how to create really super hydrophobic coating of some ceramic type material, durable ceramic, so that water and other stuff does not stick at all, and you don't have to clean. Okay, and so just switching gear a little bit, I'm going to spend just a couple of minutes on water treatment. This is not water conservation. Now we are talking about water treatment. Titanium oxide, dioxide, is a well-known material, N-type semiconductor with excellent photocatalytic properties near UV, and it decomposes a lot of organic stuff and kills bacteria and so on. Now the problem is UV tends to penetrate into DNAs and damages some of the cells. And also, if you can only use UV, it's not practical enough. You should be able to use the whole spectrum of sunlight. Okay, so there are ways people have done research by doping titanium oxide with the carbon, nitrogen, and so on to broaden this spectrum so that much of the sunlight spectrum can be utilized for treatment of water. Okay, so it is known that titanium oxide people use particles more often, but one of the approach that we are using is, make this special nanotube type structure. And if you calculate the surface area, this is like a ceramic tubing, but nanoscale. It's only about 100 nanometer diameter and 300 nanometer tall. And if you calculate available surface area, this is like 13 times higher than standard flat titanium. So the game here is, reaction, the total surface area, you increase it by a factor of 10, 20, and that way you can make the kinetics that much faster. But this is an actual scanning electron microscope picture of showing nanotubes. This cross-sectional picture showing about 100 nanometer. The wall of the tubes are about 10 nanometers. Extremely small configuration. And what we are trying to do is to build like three-dimensional structure. Okay, and suppose you have a glass or any substrate, you build nanostructure cones like this. Okay, we can easily do this. And then we add these titanium oxide nanotubes on top. So schematically shown here, you have the cone and you grow all these nanotubes. So you add this and this, you have extremely large total surface area. And then we build a structure of this nature. And this is like if you want to do all season, during the daytime, we would like to have sunlight come through and do the water cleaning and the water treatment. But at night, you have a lamp here which operates and makes this catalytic reaction continue. So you could, in principle, do 24 hours a day water treatment. So the name of the game is one could increase by nanotechnology the available surface area of a reaction much more. Okay, so that's pretty much the end of my talk, and I'd like to acknowledge contributions by my graduate students and the support of the work by the UAMA fund at UC San Diego. Okay, thank you very much.
So the next speaker is Peter MacLaggan. He's the Senior Vice President for Project Development at Poseidon Corporation, who are involved in a desalination plant to be constructed at Carlsbad. And it's a great pleasure to have Peter here to give his industrial perspective on this issue. So.
Thank you, Paul. Good afternoon, ladies and gentlemen. I want to speak with you this afternoon about the Carlsbad Desalination Project, but more importantly, the fact that the San Diego region, for the first time in a large-scale fashion, is looking seriously to the Pacific Ocean for a partial solution to our water supply needs. And this has been done, as we all know, throughout the world. There are currently 20,000 operating reverse osmosis seawater desalination plants operating across the world, producing over 3 billion gallons of water every day for every conceivable use of water, from agriculture to industry to residential uses, so on and so forth. So we know it works. What you may not know is that this technology is San Diego home-based technology. And it goes back to the Kennedy administration, where we had an administration, a president that was very keenly focused on the need to lower the cost of desalination to prevent what he thought was going to be the next world crisis, was over not oil but water. And so that administration started an R&D effort that sent money to General Atomics here in San Diego County that commercialized the reverse osmosis technology that had recently been discovered and advanced at UCLA. And lo and behold, we now have an industry here in San Diego County that produces about $300 million worth of goods and services that serves all these plants all over the world. Yet we don't really use it here at home for our water supply. We use it for purposes of industrial water purification and producing high quality water for the pharmaceuticals, biotech industry, and the electronics industry, and for our power plants and so on and so forth. But what we're looking at today in Carlsbad, and shown in the artist's rendering, is our first full-scale water supply. And the goal here is to get about 10% of our future water from the Carlsbad Desalination Project, 56,000 acre-feet of new water. It will be essentially a drought-proof supply because we're drawing from the largest reservoir in the world, and we know it's not going to dry up. If it is, we've got larger problems to worry about. In fact, some have suggested that maybe this is a way to mitigate global warming, is to produce some water from the ocean and reverse some of that sea level rise that's projected to occur. What we have is the project is being advanced through a public-private partnership, and the Poseidon Resources, my company, is working in partnership with 9 local water agencies that have subscribed to purchase the entire output of this plant for the next 30 years. So the plant itself is fully subscribed. It's been that way for at least a couple years now. You have on the map in front of you indication of who all the participants are in this project, and the city of Carlsbad, first and foremost, will be taking 40% of the plant output for their largely almost 100% of their potable water supply, and then stretching from Oceanside all the way up into the I-15 corridor, Rainbow Valley Center. The agricultural sector will be taking, each of those agencies will be taking about 7,500 acre-feet of the output, or 15% of our production. And then we have other coastal communities, the cities of Encinitas and San Marcos and Escondido and Rancho Santa Fe, Solana Beach, all have subscribed to receive part of the output. And then we have water flowing all the way down to Chula Vista and National City and the Sweetwater Authority. So one thing that's very clear is this project has broad regional reach, and it truly is regional in its scope and nature. And the relationship between the public agencies and Poseidon is that it's Poseidon's responsibility to build, own, operate this plant and then sell the water to the public agencies at a price not to exceed what they otherwise would have paid for the imported water they no longer require, plus a financial incentive that's available to them from the Metropolitan Water District to help encourage local supply development to overcome some of our water supply issues here in Southern California. So from their perspective, what we have is a new water supply that's more reliable than the one they have today, in that it's coming from a source that's essentially drought-proof. So it gives them a bucket to draw upon that will be available when we have cutbacks, and help stretch the water a little further here locally by making the overall pie or sources of water we have available to us more diverse and larger in quantity. And it's also somewhat higher quality water that the reverse osmosis technology, by removing the salt, you have to remove all the other impurities, and you end up with a very high quality water, which is a good thing for residents and businesses as well. The need for this is probably very clear to everybody in this room, but let me just take us back to our last time we were talking about cutbacks in water supply in 1990-91 timeframe. At that time, 95% of our water supply came from 2 sources, the Colorado River and the State Water Project. So 95% of our water came from outside the area. If you go back just 60 years ago, all of our water came from within. And so we have gone in a period of 60 years from totally self-dependent on local sources, where we provided all our water from within, to 95% coming from outside the area, and then those sources subject to intense competition by fish and other residents in other states like Arizona and Nevada, the central part of California. All of us share these common sources, and today we have a situation where those of us on a coast need to look at diversifying our supply and making it more reliable in the process. So what you see is, in the bottom pie chart, is where things are headed by 2010, where we will be as a much more diverse water supply portfolio. We have done that through conservation, recycling, negotiating water transfer agreements with the agricultural sector, lining canals in the Imperial Valley, and then the seawater desalination component is expected to pick up about 7% of our need in this region. Now, just 5 years ago, there was the final settlement of a lawsuit over the Colorado River, which is our largest supply, a lawsuit that started in 1963, but that resulted in Southern California, the coastal plain of Southern California, losing about half of its Colorado River supply. And today, of course, we have a situation where our other major source of imported water has come under tremendous pressure resulting from endangered fish that reside in the vicinity of the pumps that move the water from the Sacramento-San Joaquin Delta down to our point of use down here in Southern California and everywhere up in between in the Central Valley, along with the fact that we haven't had sufficient rain or snow in both watersheds, Colorado River as well as the State Water Project for several years now. So the pressure is on. There's talk again about possible cutbacks later this year. Our customers, the 9 public water agencies that we're working with, are all looking toward participating in a desalination project to help shore up the reliability of their potable water supply. They've already done many of the things that are readily available, the low-hanging fruit, if you will, in terms of conservation within their service area. And they've done quite a bit in terms of expanding the use of reclaimed water, where Carlsbad's a very good example here, probably the best example in the county in terms of a city that has gone the extra mile to diversify their supply, and that they have just completed a $50 million project to build this large modern water recycling system that has 3 sources of supply feeding into their city, and they're now getting almost 20% of their water. So 1 out of 5 gallons of the water that's used in that city is used outdoors for irrigation. It's water that's been recycled. So what they're trying to do through the Carlsbad Desalination Project is just shore up the potable water side of the house, the water you use indoors and for business and for industry, and how to make that as reliable as possible through coming up with some additional local sources. We are located at the Encina Power Station, and so what you have in the graphic that's before you is a schematic of the power plant, how it interacts with Agua Hedionda Lagoon, and the desalination facility. And just to follow the water, we have the Pacific Ocean out here, an opening to the Pacific through which the water comes across the lagoon. Today it flows through the power station and then right back out to sea through the channel in front of the power station, and that's how they cool the steam that's produced to generate the electricity. When they're all done generating electricity, they need to condense that steam back to water, and they do that with a big radiator that's cooled with seawater. So we have a ready-made source of water available to the desalination facility. We take 2 gallons of seawater to produce 1 gallon of drinking water. So you start with 100 million gallons a day. You filter it several times, push it through a reverse osmosis membrane. 50 million gallons comes out as high purity drinking water. You have another 50 million gallons of seawater, which is now twice as salty as it was when you began, because you've extracted half the water. So that salty water goes back into the Pacific Ocean via the discharge channel from the power plant, and out to sea it goes. The power plant normally, when it's operating, is flowing enough water that water is diluted to a level that's acceptable for the fish and other marine organisms that reside out there, so they won't be impacted. But we've been issued a permit by the Regional Water Quality Control Board that ensures that if the power plant's not moving enough water, that we have to make sure that we have, for every 1 gallon we bring into our plant, another 2 gallons available to dilute the salty byproduct of the process going back. So we're no more than 20% over the salinity of the ocean when the water leaves the property, and that's what has assured that we can maintain and protect the organisms. And the reason why we know that is because we've had a test facility operating up on the site for 6 years now. We've been working very closely with some of the scientists here from the university at Scripps Institute of Oceanography and others to help us confirm and produce some very high quality science that demonstrates what are the tolerances to marine organisms, to salinity, and specifically those organisms that reside in the vicinity of this project. Of course, the power station provides a great location for such a project. It's appropriately zoned. It's a public utility site on the coast. And if we can combine those uses and do it all on the same property, that means less property taken up for that kind of utilization along our precious coastline. We have analyzed and permitted the project for 2 operating scenarios, one when the power plant is operating and another one when it's not, and received approvals to operate under both conditions. This is again, an artist rendering of the facility itself, a bit of a sketch to show you what the technology would look like when it's finished. We bring the water up from the power station. We hook into the discharge channel of that power plant. We bring up 100 million gallons. We run it through some coarse filters that will remove all of the larger organic particles and seaweed and what have you, shells, and those are strained out the front of the building right in this area. We then go through a finer filtration process to start removing the suspended organic silt and sand, other things that would be harmful to our membranes. The membranes are in these stacks, and a reverse osmosis membrane is a very fine piece of paper. It looks like photographic paper with a glossy film on it, and under pressure you can push the water through it, but the salt can't get through. And the reason why that's the case is because the surface of that membrane has little tiny holes in it, just much like the professor was talking about, nanoscale surface that allows water to pass through, but the salt ions are too large and they can't get across this membrane. And so if you can imagine that the holes of that membrane were about the size of an opening in a tennis ball can, say 3 inches in diameter. On that same relative scale, a water molecule would be about the same size as a tennis ball, and under pressure, you could push it through the membrane. Under that same scale, a salt particle will be about the size of a tennis ball, not a tennis ball, a softball. And for the same reason you can't put a softball in a tennis ball can, you can't get it through this membrane. Now the professor's gonna, if he was up here, he would criticize me for this oversimplistic description of reverse osmosis, and it truly is, but that'll give you a mental picture as to how this process works. You apply pressure to a membrane, water permeates across, salt can't get through, and in the process of doing so, we remove all the other contaminants as well, because on that same relative scale, the tennis ball, the softball, if we were looking at a virus, it would be about the size of a semi-truck, and a bacteria would be as large as this room, and so on and so forth. So if you're getting the salt out, which you can measure on a real-time basis, you're also removing all of the other impurities that you would be concerned about. Well, where are we in the process? We've been at this for 10 years, and we've been in permitting for over 5 years. We have secured all of the necessary approvals but one. There's a hearing in April before the Regional Water Quality Control Board to sign off on a wetlands mitigation plan that has been approved by the Coastal Commission and by the State Lands Commission, and now it's time for the Regional Board to act on that as well, which we expect they will in April. That will bring to close the permitting process, and from there we go on to preparing for construction that we expect to start in the third quarter or the fourth quarter of this year. It will take 36 months to prepare that plant and producing water that's meeting all of our contract requirements, and from there it flows out into the system starting in 2012 and for the next 30 years thereafter. Just to summarize a couple of key points, this project is far more than just a water supply project. It's also an environmental restoration project. It involves 55 acres of marine wetlands restoration, and it also involves an effort to ensure that we can advance this project in a fashion that will make sure that we don't contribute to global warming, which is that we will be offsetting our net increase in energy usage through our, we don't produce greenhouse gases as part of the desalination process, but we do buy electricity from San Diego Gas and Electric. So that incremental increase in the energy that we use over that would otherwise have been required for importing that water that no longer will be brought into San Diego County will be offset through the purchase of renewable energy credits and carbon offsets and what have you. We also have gone to great lengths to ensure that all the equipment in the plant is the highest efficiency available in terms of pumps and motors and other technology. We're going to be restoring some wetlands that will sequester carbon. We've committed to plant $1 million worth of trees up in the burned out areas of the Cuyamaca Forest to help sequester carbon, and we're looking at installation of a solar array on top of the plant to provide part of our energy to fire the facility. Just to summarize, 56,000 acre feet of a new water supply for the San Diego region, delivered on a wholesale basis to 9 retailers who are looking at a goal of drought-proofing their systems, providing a reliable, high-quality supply for their customers. We have a commitment to maintain, restore, and enhance Agua Hedionda Lagoon, which is our source water. We think that source water protection and providing drinking water supply begins with the watershed, so we're going to be working hard with the local community to ensure that Agua Hedionda Lagoon continues to be the pristine water body that it has been for the last 50 years, and pick up on the stewardship on that for our time in operating the plant. We have 55 acres of wetlands restoration, another 15 acres of lagoon front property that will be dedicated to the public to restore and enhance a fish hatchery to expand the Hub SeaWorld White Sea Bass Fish Hatchery, and to provide property for public access, fishing and recreation and so on along the lagoon. And as I mentioned, a climate action plan that will ensure that we do all this and not contribute to global warming as part of the project. Lastly, as I mentioned, we've got a big industry here in San Diego County that's going to be part of this project because they provide the goods and services we need. We expect during the 2 years that we'll be under construction that we'll be able to keep about 2,100 folks employed, and after we're up and operating, the direct and indirect and induced employment associated with this project and its annual operating budget will be about 400 jobs. So with that, Paul, I'm going to close right here, and I thank you all very much for your attention.
We now have two respondents who will make some remarks on the things they've heard. And the first of these is Philip Anthony. He's been on the Orange County Water District Board since 1981 and was the director from 1992 to 97. So, Philip.
It's a pleasure to be here. I think this is an exciting kind of a function to be putting on, and I commend your group here at UC San Diego for doing it. I got a couple of confessions to make. I'm an elected official. That means politician. I'm a politician. And any other politicians in the room? Good, one's enough for any meeting. But I am an elected director, elected official to this big water district in central and north Orange County. And I've been there a long time. And I just want to make a point that you've heard an interesting story just a minute ago about what Poseidon's doing. But that wouldn't have been possible unless the elected officials of several cities and several water districts agreed to buy in. So most of your water activities, believe it or not, and just think about it, are controlled by elected officials. City council members over your city water departments, county supervisors over various county functions, many elected water district board members. They pretty much make the final decision on what's happening. Even your big San Diego Water Authority, which has concerns and control over the entire county, those people are not elected to the authority, but they're elected to some water district or city that appoints them to the authority. So all those folks are elected officials. And part of my little quick story today is just to make you aware of that, because so many things we try to do in the water world, whether it's local districts or regional or even statewide, those doggone politicians have got a say in it before it's said and done. And that's very important because, number one, those politicians do answer to you, you the voters, so they have that concern. But a lot of them aren't really particularly experts in what they're doing. Now, I'm different. I'm actually a scientist by trade. I'm a master's degree in physical chemistry, so I get the added fun of enjoying and understanding some of this stuff that we're doing, like Peter was just describing. So that's one of the reasons I've stuck around so long, because we have done a very important project with my district, which is a cousin to seawater desalination, but it's that dreaded toilet-to-tap game that you tried to play in San Diego 10 years ago and got destroyed, but now it's making a comeback. My district, and we've done this actually since 1975, we take treated wastewater from a very big sanitation district right next door to us. We both actually serve 2.25 million people in North Orange County, the same people. They collect the sewage and treat it. We manage a groundwater basin. By the way, my district manages a groundwater basin first and foremost. Now, we're lucky in North Orange County, we've got a very good groundwater basin. San Diego, virtually none. South Orange County, virtually none. But from about the El Toro Y, Irvine, on north in Orange County is a very good groundwater basin. Now, we manage that so intensely. It's probably the most intensely managed basin in the world that we provide 2/3 to 3/4 of the water for 2.25 million people that are on top of that basin. Now, that's wonderful, but even that is not enough to keep up with the demand. So we've been facing the same problem you face here, a little different quantities and amounts to it, but we have been using that basin to the hilt. Unfortunately, it's also connected to the ocean underground, so you put the basin down too far, and guess what happens? The seawater comes running in. Funny how that happens, isn't it? That happened really bad up there in the 1950s and 60s. We still had agriculture sucking up water, pumping out of the ground, population growing, a few dry years, and the seawater came in, 4, 5, 6 miles inland. knocked out all the wells in Newport Beach. Those rich people couldn't pump their wells. They were full of salt water. Knocked out a number of wells in Huntington Beach near the ocean. And it caused a deadly problem, losing those wells, but also a threat, because that water could keep coming in. Now, my district was worrying about that, obviously, this was before I was on the board there, but they launched the world's first big RO plant in 1975 to take treated wastewater, clean it up through RO to make it better than drinking water. It's virtually distilled water. And they started putting that water into the ground through injection wells to make a barrier underground to keep the seawater back. Now that saved the basin, and we're doing that to this very day. But after the last nice drought around here back in the early 90s, we had that drought from 87 to 92, we were realizing, and I was there then, that we needed more water. That seawater barrier was barely keeping up with the demands on it. And plus we had growing population, we had the problem of the imported water not being totally reliable, because even though we had this great groundwater basin, we still had to have about a third of our water imported in. Down here it's 90%, South Orange County is 90%. Even in our nice groundwater-rich area, we still needed about a third of our supply to be imported. So look what's happened here in Southern California. The second and third largest counties in this great big state, over 3 million people each, we built this huge civilization on imported water. And that imported water is going away, and that's a scary situation. So I think your theme tonight is perfect. New sources of water. We've got to have them, or else we're all going to move back to the Midwest or someplace else. Maybe we'll all immigrate to Mexico. If the imported water supplies keep getting worse, we're going to be in even more trouble. But even if they sort of hold on, we're still in need of more water. And as was mentioned earlier, we're losing more and more water from the north, from the Delta. The Colorado River supplies were cut back. They're being brought back a little bit by horse trading water with the farmers and that kind of thing. But the supplies aren't getting better, the imported supplies, and they're still in great threat. So what we did to deal with that problem back in the early 90s, we looked at all the possible sources of new water. We looked at more conservation, which is wonderful, we need that, but that's never enough alone. We looked at desalination. We looked at buying more imported water, but we knew that was risky, if not impossible. And we looked at doing more of the water recycling of wastewater to drinking water. So we started then and began working on a new, bigger plant to do the thing we've been doing since '75. Unfortunately, we're getting ready to go into design. You folks in San Diego had this huge, political, ugly battle of fighting over toilet to tap. And the election of '98 pretty much killed it. The city quit and gave up. And here we were trying to do basically the same thing, except we weren't going to put the water in the reservoir, we were going to put it into the groundwater first, which is another barrier between the toilet and the people. But anyway, we went ahead and did it. And because of what you did here, I launched an intensive public outreach campaign for over 10 years. And we went to the people and told them the story, the whole truth, from the toilet to what happened in between to what happened to the water. And we ended up getting tremendous support. We went to all the elected officials, from the council people to the state people to the congressional people, and got support. All the community leaders, all the environmental groups, they supported us. Even to this day, no organized opposition. And luckily, we're something that you can follow. The city of San Diego is now trying to bring it back again. They've launched, as you might know, a small test program to do the same thing they tried and failed in the 90s. Helix Water District, east of San Diego, is just starting to do it. City of Escondido is just starting to do it. And that's because it's a pretty sensible thing to do. The wastewater is always there, just like the ocean. If you've got people, you got wastewater. And you've got a way, using reverse osmosis, to take that water to virtually distilled water quality. And that's what we do. And that plant is real. It's been operating for 14 months now. Since January 10th of 2008, it's been going. And it's had no problems. We test the water, hundreds and hundreds of different tests, and never a problem. And you're invited to come up and see it, and I urge you to do it. It's only an hour and a half drive from here in Fountain Valley in Orange County, but we welcome tours. People are coming to this plant from all over the country. We've got a group from Escondido coming up next week. They've come here from Singapore to copy it, from several places in Australia, and it is one of the ways that we know we can make new water, and we do need it. But thank you. It's a thrill to see this happening. I encourage you to keep going. It's a wonderful program you're doing. Thank you very much.
So finally, I'd like to introduce Jeff Mosher, who's the Executive Director of the National Water Research Institute here. So.
Okay, well, thank you for the invitation being here. I think you should be commended for addressing these topics. I know previous forums have looked into the link between energy and water. It's a real one. It takes water to make energy, and vice versa, it takes energy to make water. Just a little bit about my organization. It's a nonprofit. Our members are water and wastewater agencies in Southern California. In full disclosure, Orange County Water District is a member agency of ours. Phil sits on my board of directors, so I have to watch what I say here today. What I would like to do is maybe talk about some broad themes briefly. And the first I'd like to address is the idea of this role for research. Here we are at UC San Diego. A lot of research takes place here. One of the things I'd like to remind you of is that we are able to do projects like indirect polar reuse with membranes because of advances in research on those membranes. That research has brought the cost down to operating those membranes to a point where those alternatives are cost equivalent to other sources of water supply. That's why we're talking about reuse projects. That's why we're talking about desalination projects, is that the barrier isn't so much the cost anymore. It might be some of these other issues related to public acceptance, related to impacts on the environment, related to energy requirements and greenhouse gas production. Those are really the issues that we're debating some of these alternatives over. There is a need for new and innovative technologies. We heard from Professor Jin about the idea of nanoparticles and nanomaterials. That holds the idea of making a quantum leap in how we treat water. We can make small increases and we can have some benefits there, but what we're really interested in is be able to reduce the energy requirement in half or a fraction of what it requires now. That would be a significant improvement. There are other things that we can think about, using things like microbial fuel cells to treat wastewater, which does two things. It treats the wastewater, but it also produces energy. When you think about wastewater, there's actually three things in it that are very good. You have water. If we can get that water out, we can use it. It has nutrients in it that's used for fertilizers, and it also has energy in it. If we can create the energy from the organic matter in wastewater, we'll have a source of energy as well. There's other things that are emerging. Professor Jin talked about nanomaterials. We are putting those things in lots of things. We're putting them in eyeshadow. We're putting them on pajamas for kids as flame retardants. Those things are going to get in our water supply. So we're talking about things like pharmaceuticals now that are in our water supply. We are going to see nanomaterials in our water supply as we have detection methods to be able to detect them. So we need to be able to have technology to be able to treat for those as well. The second topic I want to mention is the idea of good science informing public policy. I work on the science side. I work with a lot of researchers. The idea that we have a lot of knowledge out there from a technical and scientific point of view that has to get into the public decision-making process, and that our public policies are based on sound science. Indirect polar reuse is provocative. The projects have a lot of barriers, from the use of advanced technologies to the need for public acceptance. There are issues there that have to be informed by the science behind them. On desal projects, we talk about the energy required. We talk about potential environmental impacts. We need to look at the science and be able to base our public policy decisions on whether to move towards desal projects, recycled water projects, based on the fundamental science. These projects are highly regulated. The regulators ask very difficult questions that sometimes we don't have all the answers. So we have to be able to make decisions in light of maybe not as much data we have, but the bottom line is we have to get that science and that understanding to be able to support these types of projects. One of the things that we're doing at NWRI is we put together a program, we put together advisory panels. We've done one for Orange County Water District's groundwater replenishment system for the past several years. We bring in experts and look at these tough questions. The regulators are invited to come into our meetings, but we're also doing one for the city of San Diego on their indirect polar reuse project. The last thing I'll say is that these projects do have a lot of benefits. When you control your local water supply, That improves your reliability. The last thing I'll say is that you have to reach out to stakeholders. These projects have to be supported. You have to gain that public support. That involves embracing the opposition and understanding their concerns. So that's a big part of moving these projects forwards. So I'll stop there and we can move on to the question and answer.